This is the 8th in a series of resources that look at matrix algebra. We define and provide basic information about matrices. We consider the operations that allow us to manipulate matrices. We discover how to use the row operations to solve a system of equations using matrices. We consider various operations on pairs of matrices, including adding, subtracting, linear combinations, and multiplying. We learn how to find the inverse for a matrix. We discover the determinant for matrices and learn how determinants allow us to solve systems using Cramers' rule. In the previous resource in this series, we discovered how to find the determinant of a 2 by 2 or a 3 by 3 matrix. But what can we use the determinant for? One use of a determinant is called Cramers' rule, which provides us another method for solving systems of equations using matrices. This method works for systems of equations with any number of variables, but we will consider systems containing 2 or 3 variables. Any system of equations with 2 variables can be written as a sub 1 x plus b sub 1 y equal to c sub 1 and a sub 2 x plus b sub 2 y equals c sub 2. Cramers' rule says that the variable x will equal d sub x divided by d, and the variable y will equal d sub y divided by d. If we have 3 variables, then we have the system a sub 1x plus b sub 1y plus c sub 1z equal to d sub 1, a sub 2x plus b sub 2y plus c sub 2z equal to d sub 2, and a sub 3x plus b sub 3y plus c sub 3z equals d sub 3. In this case, the variable x will equal d sub x divided by d, the variable y will equal d sub y divided by d, and the variable z will equal d sub z divided by d. But how do we find these d's? The basic method is the same regardless the number of variables. First, we need to find the d, which is the determinant of the coefficient matrix, which is formed by the coefficients of the equations when expressed in standard form. Then, for each variable, we replace the column of its coefficients with the column of the answers from the equations. We find the determinant of this new matrix. Then we complete the appropriate division to solve for each variable. Let's see some examples. Suppose we have the 2-variable system of equations 3x plus 2y equals 43 and 4x plus 5y equals 83. First, we need to find the determinant of the coefficient matrix. We want to find the determinant of 3 and 2, then 4 and 5. We have 3 times 5 minus 2 times 4, so our value for d is 7. Next, we want to find d sub x. We replace the first column with the solutions, so we will be finding the determinant of 43 and 2, then 83 and 5. We have 43 times 5 minus 2 times 83. So d sub x equals 49. We also need to find d sub y. We replace the coefficients for y with the solutions. We find the determinant of 3 and 43, then 4 and 83. This gives us 3 times 83 minus 4 times 83. which equals 77. To solve for x, we divide d sub x by d. This is 49 divided by 7. X equals 7. To solve for y, we divide d sub y by d. We have 77 divided by 7. Y equals 11. What if we have three variables? Suppose we have the system of equations 3x minus 2y plus z equals 16, 3x plus 3y minus z equals negative 7, and x plus 4y plus 3z equals 2. First, we need to find the determinant of the coefficient matrix. 3, negative 2, and 1, then 3, 3, and negative 1, then 1, 4, and 3. We will make our lives easier and use the shortcut method. We place copies of the first two columns to the right of the matrix, so we now have 3, negative 2, 1, 3, and negative 2, then 3, 3, negative 1, 3, and 3, then 1, 4, 3, 1, and 4. We multiply to find the top-down diagonal products. We have 3 times 3 times 3 to get 27. Negative 2 times 1 times 1 to get 2. 1 times 3 times 4 gives us 12. We also find the bottom-up diagonal products. 1 times 3 times 1 is 3. 4 times negative 1 times 3 is negative 12. 3 times 3 times negative 2 is negative 18. Adding the top-down products and subtracting the bottom-up products, we have negative 27 plus 2 plus 12 minus 3 minus negative 12 minus negative 18 gives us a determinant of 68. We also need to find each of the determinants for the variables. First up is x. We replace the x coefficient column with the solutions and have 16, negative 2, and 1, then negative 7, 3, and negative 1, then 2, 4, and 3. We copy the first two columns to get 16, negative 2, 1, 16, and negative 2, then negative 7, 3, negative 1, negative 7, and 3, then 2, 4, 3, 2, and 4. We find the diagonal products and add or subtract them as needed. We have 144 plus 4 plus negative 28 minus 6 minus negative 64 minus 42. Combining, we find the determinant for the X matrix is 136. Now we will find the determinant for the Y matrix. Replacing the Y coefficients with the answers, we have 3, 16, and 1, then 3, negative 7, and negative 1, then 1, 2, and 3. Copying the first two columns, we now have 3, 16, 1, 3, and 16, then 3, negative 7, negative 1, 3, and negative 7, then 1, 2, 3, 1, and 2. Finding the diagonal products gives us negative 63 plus negative 16 plus 6 minus 144 minus negative 6 minus negative 7. So the determinant is negative 204. We also need to find the determinant for the Z matrix. Making the needed replacements, we have the matrix 3, -2, and 16, then 3, 3, and -7, then 1, 4, and 2. Adding on the copies to the end gives us 3, -2, 16, 3, and -2, then 3, 3, -7, 3, and 3, then 1, 4, 2, 1, and 4. Finding the diagonal products, we have 18 plus 14 plus 192 minus 12 minus -84 minus 48. This gives us the determinant equal to 272. Now we have all the information we need to actually solve for the variables. Recall that each variable is equal to the determinant of its matrix divided by the determinant of the coefficient matrix. So we have x equal to d sub x divided by d, y equal to d sub y divided by d, and z equal to d sub z divided by d. Solving for x, we have 136 divided by 68, so x is 2. Solving for y, we have -204 divided by 68, y equals -3. Solving for z, we have 272 divided by 68, z equals 4.